on to our final speaker for the event. So we have TJ McKinley. He's going to be speaking to us about the work that they've been doing on trying to use uncertainty quantification methods to model COVID. So I think I've said your talk title horrendously badly, TJ.
No, that's fine.
So it's quite nice. I think today, like yesterday, we top and tailed with education, and it's quite nice today that we're top and tailing with the more statistical methodology part of the consortium. So with that, I will pass over to you, TJ.
Brilliant. Can you see my screen? Is that?
Yeah, that's perfect.
Okay. Thanks very much, Kira, and thanks everyone for coming. I have a friend who's an ecologist who always laments that mathematicians are rubbish at coming up with pithy titles for their talks, and unfortunately I seem to have fallen foul of that particular stereotype here, so I apologise for the rather unwieldy title, but hopefully it sort of does what it says on the tin. I should say at the beginning of this talk, I mean, I've been kind of in awe really of the way that the epidemiological community have kind of stepped up to the mark with regards to modelling the pandemic. And I think it's really testament to, I mean, all of the amazing work that's been presented over the last couple of days, but also not only just within JUNIPER, but also within other modelling groups is really inspiring. And I think it's fantastic. And I feel slightly then under the feeling that what I'm going to present here is slightly underwhelming compared to all of that good work, because I'm not going to give any results. But in our defense, this sort of project that I'm going to be talking about today was really set up with an eye on more on developing and pushing methodology that would enable us to be able to do things perhaps slightly differently next time round. So rather than being reactive to the current pandemic. So with that in mind, I should also say that this work is not my work alone. There's a wide group of people listed here who are all involved in one way or another. And so really the kind of problem here is which Chris gave a really nice introduction to earlier, is the problem of performing statistical inference for complex models, so particularly fitting models to data and estimating parameters. And this is hugely complex for various different reasons, but principally because we have a paucity of necessary data. So the models that we're developing are often depend upon things that we don't observe, like infection times and those sorts of things. And so in a sense, it becomes a massive missing data problem to deal with. And this is then further compounded by the fact that the models themselves are very complex. And again, particularly as we've seen with models that have been developed during COVID, we often are beginning to push models into building more complicated models, and that means that we have more parameters that we're trying to estimate, and we also might want to integrate more sources of data, and all of these things kind of compound to make the inference side of things very difficult. And all of this comes to a head, of course, if you want to do real-time model fitting. And the reason for this is because the gold standard inference algorithms that we use are typically very computationally intensive. And so that then means that they're quite difficult to scale and they're quite difficult to generalize. And so this is a particular problem. There does exist some software for calibrating epidemic models, but at the moment that these tend to have sort of limited flexibility. So often they're restricted to single populations, for example. And they don't always have native support for, parallelization on different architectures and things like that. There is some really kind of, I think, interesting pieces of research that are going on. So in particular, the stuff that Chris was talking about earlier, that him and Alison Hale and various others are working on this GEM software. And I think this is incredibly exciting and could be a real step forward in being able to implement scalable and flexible inference algorithms. So I think that's really, really exciting. But I also think that there is a tract as well, or some utility in developing inference algorithms for where modelers can implement their own simulation models. So many epidemiologists will develop their own kind of model. And so there is also a kind of a suite of statistical techniques that have been designed where you can use those simulation models directly within the inference routine. And all of these different approaches have their own sort of benefits and challenges. But in general, the simulation model approaches are in general sort of easier to adapt. So if you want to build more complexity into your model, that's generally more straightforward, but that's offset against being generally very computationally demanding to run. And so typically, if models are being fitted in real time, this often requires either some form of approximation or some form of simplification of the models. And I sort of very much adhere to this kind of idea that models should be as simple as possible, but no simpler. And so sometimes there might be sort of policy questions that might require us to have a more complex model than we would ordinarily want to develop. And so what we're trying to do here is trying to sort of bring techniques that have been developed in other fields for fitting complex models and trying to see whether they are feasible for epidemic systems. So in particular, the motivation was this piece of software called MetaWards. And so this came out of a nice paper by Leon Dannon and Thomas House and Matt Keeling a few years ago. And Leon got a grant to turn this kind of model into a piece of software. So this is a flexible framework for developing spatial stochastic metapopulation models. It's written in Python. And the idea is that it's very similar, I think, in essence to Chris Jewell's modeling approach, and also Chris Davis was talking about before. So it's a metapopulation model. We're modeling it at the electoral ward level. And wards are coupled together according to commuting data. And so that enables individuals in the model to move between different wards. And so you can have a spatiotemporal spread driven by commuting patterns. And the software allows you to write relatively general epidemic systems. So it recently has more support for things like multiple epidemic pathways. You can model different demographics. So that means that you can add age structure and things like that to the system. And so we've been kind of working with this and trying to develop a model, and then also to help sort of, so we've also been trying to amend the software to do things like potentially model multiple strains and other bits and pieces. If anyone is interested, then there's really nice documentation at metawards.org for how to do this. So this is, like I say, a Python package. So this is a kind of brief model structure that we're sort of working on at the moment. The model is still under development, but it's essentially a sort of SEIR type model. We have a sort of asymptomatic pathway here, a symptomatic pathway, and then we also have some symptomatic individuals that go into hospital. And we have different transitions, and we have some of these transition probabilities are age dependent. So particularly, your likelihood of going into hospital and things like that is heavily age dependent. And we also have age dependent mixing in the transmission term. If anybody is interested, all of the sort of background and documentation for the model can be found at this website, and we are sort of actively developing it as we're going on. To give you just so this is just a single simulation from the model. It's not a fitted model or anything like that, but you can see that there's quite a fine spatial resolution that the model is capable of running simulations over. And so this is the kind of challenge that we sort of set ourselves, is how do we take a model that has this kind of spatial resolution and try to fit it to data. So as I said before, we've got lots of so various parameters. Some of them are age dependent. We've got 8 age classes in our model. We also have some non-age specific parameters, so things like R0 to the length of the incubation period and so on and so forth. And the main statistical challenge is how do we calibrate this model to available data? And so we're particularly thinking about death data at potentially either the NHS Trust or LTLA sort of levels. And so the problem here is that we have a sort of relatively high dimensional parameter space. And so what we need to do is robustly explore that parameter space in order to be able to find model fits. And then what we want to do is propagate the uncertainties through to predictions. So the problem is that this model takes a very long time to run. So we're talking about order of tens of minutes per simulation. And so this puts a heavy constraint on the number of simulation runs that we can do. And so what we need is a method. So again, usually when you go to high dimensional parameter spaces, in order to explore those spaces, you would run your model for lots of times across that space. And here we can't do that. And so that's the main sort of difficulty. So we need a way of being able to efficiently explore that space. And so what we're doing is appealing to the use of emulators. And so an emulator is effectively a statistical representation of a complex model, which I'm going to call the simulator here. So the idea is that we can run our simulator at different parameter sets, and we can get some outputs. And then we model those outputs using some kind of statistical model. So usually a sort of a Gaussian process regression model or something like that. And then we use the emulator as a surrogate model in place of our simulator. And so the idea is that the emulator is an approximation, but it's very, very fast to evaluate, which means that we can run it a large amount of times. So just to give you a kind of, so this is a toy example, but just to kind of make clear what we're sort of trying to do. So if you imagine that we've got in this case, I've got a single parameter model. So I've got the parameter range on the x-axis here. And what I can do is I can plug a parameter into my model and I can get a particular output. So the y-axis here could be some output that we're interested in, like number of deaths or something like that, okay? And the simulator is expensive, so I can't run it at all parameter sets. So I run it at a range of parameter sets and I get a range of different outputs. And so then the idea is that I fit some kind of regression type model usually to these outputs from my simulator. And once I've trained that model, I can then use that emulator to predict at all of the parameter parts of the parameter space where I haven't evaluated my model. So in this case, this is a Gaussian process that I've fitted here. And so the blue line here corresponds to the mean prediction from my Gaussian process emulator. And the red bars correspond to uncertainty, okay? And so the idea is that once we've trained the emulator, we then run it through the parameter space, and we can use that, the emulator as a proxy for our complex model. And so this potentially greatly reduces the amount of runs of our simulator that we have to do. So then the question is, how do we do calibration? So how do we fit this model to data? And the approach that we're taking is an approach called history matching. And what history matching does is it aims to, rather than try to find good parts of the space, what it tries to do is it tries to rule out bad parts of the space. And it does so by appealing to what we call an implausibility measure. And so just to sort of talk you through this equation, so the implausibility measure is a function of the parameters, and the numerator here is effectively, so if y is a data point, so we're trying to find parameters that give us runs that are close to the data. So y is a data point here. E of theta is a prediction from our emulator. So this numerator here is a measure of how far the prediction is from the data, okay? And then we divide that through by various different sources of uncertainty, but crucially, this emulator uncertainty here, okay? So essentially, it's sort of a distance divided by uncertainty type ratio. And the idea is that we keep any parts of the space where this implausibility measure is low. And the implausibility measure can be low for one of two reasons, either because the emulator produces predictions that are close to the data, okay, so the numerator is small, or if we are in parts of the space where there is a lot of uncertainty. And so particularly if we are in parts of the space where our emulator uncertainty is large, then the implausibility measure will try to keep those bits of the space if it is unsure about what's going on there. So just to give you an illustration back in our toy model, if you imagine that this middle sort of horizontal line is a data point, then what we're trying to do is find areas of the parameter space that give me something that is consistent with the data. So what I can do is generate the implausibility measure, and I can employ a threshold here where I remove bits of the space where the emulator is high, okay? And these cutoffs have some theory behind them, so there are ways of being able to choose them so that they're relatively conservative. But you can see here that in this part of the space down here, even though there is uncertainty in our emulator, the predictions are far enough away from the data that the implausibility is high, okay? As we start to get down towards the data, then the implausibility drops. And so applying a sort of threshold of 3 here, we would keep the parts of the space that are colored green and yellow, and we would remove parts of the space that are red. Okay? And we do all of this with the emulator. Now, of course, the problem is that the implausibility keeps parts of the space where there are potentially good fits or it's potentially uncertain. So typically we would go through this process through a series of waves where we add more simulator runs in this green region. Okay, so for example, I might add another simulator run here. And then I can refit my emulator, and now my emulator is much less uncertain, so it tightens up the implausibility and I can rule more space out, so on and so forth. So I can add another point here and another point here, so on. Okay, and so the idea is that you do this through a series of waves, but the history matching sort of allows you to target your simulator runs in parts of the space where you're more likely to get good fits. And once you've got a final implausibility space, then you can run your simulation model within that space to see whether or not your model fits well. And this is the kind of idea. So this process is a good way of exploring parameter space using an emulator, and it doesn't ignore the fact that the emulator is not a perfect representation of our complex model. But it also allows us to have more control over how many simulations we need to run. Okay, so we can, if you like, design it in such a way that we know how many simulation runs we're going to have to run at each wave. And so this makes it kind of easier to implement on HPCs and things like that. And there's lots of work going on to try and emulate particularly multiple outputs and how you combine emulators of different outputs together, and so on and so forth. And this kind of approach has been shown to work effectively for calibrating complex models in lots of different fields. But it's only recently that we've started to look at this in infectious disease modeling. And one of well, there are various challenges with this. So one of them is that as of yet, there is no general purpose software. So people tend to write their own software for doing both the emulation and the history matching. I'm involved in a project with London School of Hygiene and Durham University, where we're trying to develop some software for building emulators and doing history matching, and so that is potentially interesting here. But also, what's kind of interesting is that how useful these methods are is not just a function of how complex the model is, but it's also a function of the types of output that the model is giving you. So stochastic epidemic models can induce distributions of outputs that are actually very difficult to emulate using standard methods. So things like non-stationarity or multimodality and things like that. So, there's a lot of work that we're potentially having to do in terms of trying to come up with ways of dealing with these sorts of behaviors that you don't necessarily see in other types of model. There are lots of different ways to emulate. There's no general consensus. I've been involved in lots of arguments between QQ groups about what the best emulation approach is. So we're sort of trying to look at various different approaches and see what works and what doesn't work. And in particular, we've been looking at deep Gaussian processes as a potential way of dealing with multimodality and things. The other problem is that MetaWards is a really complex model. So we're getting, similar to Chris was saying earlier, we're getting like gigabytes and gigabytes of output. And so not only is the model taking a long time to run, but the post-processing is huge with this sort of, because we are effectively are trying to combine lots of information at a very fine spatial resolution. So there's lots and lots of kind of computational challenges still on top of all of this. And also we're trying to fit the model to trusts or LTLA simultaneously, which means we need to build lots of emulators. So, and in a way, this all hopefully would have to be semi-automated to make this useful in the future. And the other thing that's kind of spent quite a lot of time talking about recently is our data assimilation. So the idea of trying to build data information into the simulations in a sensible way. And I'm not going to talk about that because I'm running out of time. So just to summarize, we've got this nice piece of software that we want to calibrate. We're developing it further, but we're also trying to put infrastructure in place to try to make these approaches more useful and more applicable to people in the future. If anybody's interested, all our model runs are going up online on Jasmine, and all of the code will be available on this website. And thanks to JUNIPER and also EPSRC for funding, and to Jasmine HPC as well for providing computing power to help with this. Thank you.
Great, thank you, TJ. And I should also say, I think TJ was very modest at the beginning with his when he introduced himself. So I think that this work, even though it hasn't yet, although a lot of the work we've been talking about in JUNIPER has been very focused on the very responsive elements that many of the groups have been doing, I think a key point that I don't think I was very good at making clear yesterday was that one thing JUNIPER really tries to do is make sure that we're really linking into the mathematical modelling community, and that's why I think like the work that TJ is doing is really critical, because it's about learning from challenges that we've had throughout the pandemic. And I remember at the start a lot of people complaining that there were a lot of mathematical modelers, well, the mathematics community were complaining that better UQ methods could have been used. So basically I think that this work is very important, and it's very important for going on ahead. So I think you're being very modest TJ. So does anyone have any questions for TJ? And given that we're running a little bit behind schedule, I might move on, but I might follow up with you afterwards, TJ, because I want to know what deep Gaussian processes are.
So do I.
Yeah, well, when you find out, you can tell me.
Yeah, no, we can chat about it. It's cool.
Thanks, TJ. Oh, Matt is here. I'm going to share my screen in case Matt has to pop off to do